Today we are going to discuss Huffman coding procedure. Huffman coding procedure is very important in the case of image compression technique. It is a source coding technique. Source coding technique is actually doing for improving the efficiency of the encoding. Depending on the algorithm we are choosing for source encoding, the efficiency of the coding scheme is varied. So in this section, we are discussing how we can do Huffman coding and what is the procedure for Huffman coding. And after that, we will discuss how to evaluate the efficiency of the coding scheme. Huffman coding is a coding scheme which is based on the probability model of the symbols. For example, in most of the questions, we will be given the symbols together with their probability of occurrence or the probability of the symbols alone. Okay, here in this we have been given 6 symbols S1, S2, S3, S4 and S6 and their corresponding probability 0.3, 0.25, 0.2, 0.15, 0.05, 0.05. The first step for doing Huffman coding is arrange the symbols in the decreasing order of their probability. So I arranged the symbols. Here the symbols are given in the decreasing order. If it is not like that, we will have to arrange those symbols in the decreasing order of their probability. So I arranged the symbols in the decreasing order of their probability. It is the first step. S1, S2, S3 and S4. And this set generates the column 1. In the next step, I need to generate the column 2. For creating the column number 2, we need to combine 2 least probable symbols. That symbols will be the last symbols in the column because the symbols are arranged in the decreasing order of their probability. So we need to combine the last 2 symbols to generate a secondary symbol. I name it as sigma 1, whose probability will be the sum of the probabilities of S5 and S6, that is 0.05 plus 0.05, that is 0.1. Now I am generating the next column. In the next column also, we need to arrange the symbols in the decreasing order of their probability by excluding S5 and S6 and including sigma 1. So I am writing it is probability is 0.3 S1. For S2 the probability is 0.25. For S3 probability is 0.2. For S4 probability is 0.15 and S5 S6 is not there. Those are combined and we have the new symbols sigma 1 with probability 0.1. Now we have got the second column. Now I am generating the third column. See the third column. In order to find the third column, we need to combine the last 2 symbols of the column number 2 to generate a new symbol known as sigma 2 with probability is the sum of probabilities of S4 and sigma 1, that is 0.15 and 0.1, that is equal to 0.25. So I can generate column 3 as, this is column 3, S1 of probability 0.3, S2 of probability 0.25, then S3 probability is 0.2, but we have the new symbol sigma 2. It has the higher probability than S3, so we need to write it before S3 in order to maintain the rule that the symbols should be arranged in the decreasing order of their probability. If you need to check is there any problem, is there any error, we need to calculate all the probabilities that will result 1 in each and every column. Okay, then we need to generate the next column. For that, we need to add the last two symbols, sigma 2 and S3, and naming it as sigma 3 with probability 0.25 plus 0.2, it is 0.45. Then I am generating the fourth column, as sigma 3 is the first one because it has the highest probability. All others, S1 has 0.3, S2 has probability 0.25, but sigma 3 has 0.45. So next is S1, surely it is S1, then it is S2, that is 0.25. To generate fifth column, you need to combine the last two symbols, S1 and S2, to give the new symbol sigma 3. New symbol sigma 4 with probability 0.3 plus 0.25, it is 0.55. Now we can generate the new column. It is sigma 4 of probability 0.55 and sigma 3 of probability 0.45. We should stop here because we need to stop generating columns until we will get only two symbols because we are coding in the binary format. That is why we need to terminate this process until we will get two symbols. Or we can say that if there are 6 symbols, we need to create 5 columns. Okay, now let's see how we can encode by using this process. So the next step is, I'm drawing the code tree here. This is the starting node and we need to draw 2 branches of the tree. Left I am giving the symbol 0, this is the symbol 1, and see our last column, the fifth column, the last column, we have two symbols sigma 4 and sigma 3. So I am naming them as sigma 4 here and sigma 3. Now these symbols are secondary symbols we are generated. So we need to expand this tree from each of these nodes. Again, I am generating 2 nodes from here. Here I am assigning 0 and here assigning 1. Then we will go for sigma 4. From where we have generated sigma 4 here. Sigma 4 is the combination of S1 and S2. So I am assigning this tree leaf as S1 and this tree leaf as S2. Now these nodes are terminated because we got the primary symbols S1, S2. Okay, then here in the next branch we have sigma 3. So sigma 3, we need to branch the sigma 3 again. We are assigning 0 and 1. Know that sigma 3 is generated from sigma 2 and S3. So I am assigning S3 here and I am assigning this node as sigma 2. So here also the symbols, we have got the symbol, so the tree is terminating here. Now we need to branch the sigma 2 again as we have done it before. This 0 and 1 is assigned, and just look at from where we have got sigma 2. Sigma 2 is the combination of S4 and sigma 1. So I am giving here it as S4 and giving it as sigma 1. Now here also S4 we have got, so the branch is terminated and we need to branch again 0 and 1. Sigma 1 we need to branch again and assigning 0 and 1. Then go to the steps where we have generated sigma 1. In the first column we have generated sigma 1 from S5 and S6. We are combined them and we got sigma 1. So S5 and S6. This is S5 and this is S6. See, this is S5 and This is S5 and this is S6, because sigma 1 is the combination of S5 and S6. So in all the branches we got S1, S2, S3, S4, S5 and S6. All the source symbols we have got. Now we can write the source symbols. These are S1, S2, S3, S4, S5 and S6. Now we can write code for S1. Just look at the tree. Here it is S1. So read from the starting node. This is our starting node. Read it. 0, 0. So the code for S1 is 0, 0. Then S2. Read it from the first node. 0, 1. So S2 is 0, 1. Then again read it from the S3. Read it from the starting node. 1, 0. And for S4 it is 1. S4 it is 1, 1, 0. So for S4 it is 1, 1, 0. Then for S5, let's see, for S5 we need to start from the first node. 1, 1, 1, 0. 1, 1, 1, 0. Then for S6, just go to the code tree, start from the first node. 1, 1, 1, 1. So we can write S6 as 1, 1, 1, 1. So this is the source encoded format for the given symbols with the given probabilities. If the probabilities are changed, the codes will be changed. There will be the change in the efficiency of the code. Next, we have to evaluate the efficiency. For evaluating efficiency, I am tabulating the symbols S1, S2, S3 up to S6 and their probabilities in this table. Then in the next column, I am writing all the code words which have been given by doing the Huffman coding before. So the next column, I am writing LK. LK means the code word length of each code word. Code word length means here for S1 we are using 2 bits of binary. So the LK, the number of bits or the code word length, is equal to the number of bits used. That is, here it is 2, and here also we are using 2 bits, it is 2. Here also we are using 2 bits, here it is 2. Here we are using 3 bits, here we are using 4 bits, and here we are using 4 bits. Now in the next column we have to evaluate PK into LK. PK into LK means the probability into code word length. Here 0.3 into 2, it is 0.6, 0.25 into 2, it is 0.5, 0.2 into 2, it is 0.4, 0.15 into 3, it is 0.45, and then it is 0.05 into 4, that is 0.2, and 0.05 into 4, it is 0.2. Now we can evaluate the sigma PK LK. It is known as L bar, the average code word length. L bar here, it is equal to the sum of 0.6 plus 0.5 plus 0.4 plus 0.45 plus 0.2 plus 0.2. That is equal to 2.35. It is 2.35 bits per symbol. Okay, so now to evaluate the efficiency equation is eta is equal to h of s divided by L bar, where h of s is the entropy and it is calculated as pk log 1 by pk, and L bar is the average code word length that we have calculated as pk sigma pk into lk, that is equal to 2.35. Now we have to evaluate h of s. Here I am writing the value of h of s. See, h of s is equal to sigma pk log 1 by pk to the base 2. So logarithm should be in the base 2 mode. So here pk means the individual probability. Here the individual probabilities are, we have given the individual probabilities are 0.3, 0.3, 0.25, 0.2. So we can write this is equal to, first one it is 0.3 log 1 by 0.3 logarithm base is 2 plus next probability is 0.25. So it is 0.25 log 1 by 0.25 to the base 2. Next probability is, it is 0.2. So it is 0.2 log 1 by 0.2 to the base 2 plus next is 0.15 log 0.15 to the base 2 plus next is 0.05 log 1 by 0.05 to the base 2 and plus the last probability is 0.205 log 1 by 0.05 to the base 2. Now I need to evaluate this using scientific calculator. 0.3 log 0.3 inverse equal to plus next probability 0.25 log 0.25 inverse equal to plus next probability is 0.2 log 0.2 inverse equal to plus next is 0.15 log 0.15 inverse equal to plus next probability is 0.05 log 0.05 inverse equal to plus 0.05 log 0.05 inverse. Now we have the answer 0.070086, but this answer is not the right answer because we have used the logarithm. This logarithm is base 10 logarithm. So we need logarithm with base 2. So in order to convert it into logarithm base 2, we have to divide the answer with log 2. So we get the answer is 2.328. So the answer is 2.328. Answer is 2.328 bits per symbol. Efficiency. Eta is equal to h of s divided by L bar, that is equal to h of s is 2.328 divided by L bar. We have got the L bar as L bar here. Yes, here we have got L bar 2.35. So we can write 2.35. This is equal to 0.9906. That is 0.9906. So efficiency is equal to 99.06, that much percentage. If you have any doubt regarding the calculation and procedure of Huffman coding, you just type the question in the comment box and we will discuss it later in the next video. Okay, thank you.